Right now, every atom in your body is shaking inside an invisible ocean. You cannot see it. You cannot feel it. But without it, you would weigh nothing. Light would not exist. And reality itself would dissolve. Scientists call it a quantum field, and it is the true skeleton of the universe. Today, we travel through ripples that become particles, an emptiness that pushes metal plates together, a field that hands every electron its mass, and a vacuum that may one day rewrite physics. If this kind of journey pulls you in, hit that subscribe button and like the video. It really helps us keep going. Take a deep breath. We begin. Picture an electron. Most people imagine a tiny ball, a marble so small you would need a microscope 1 billion times stronger than anything we own to see it. That picture is wrong. Every physics textbook published before 1940 taught it. Every cartoon of an atom still shows it. Yet the deeper scientists looked, the more that little ball melted away into something far stranger. There are no marbles. There are no specks. The smallest pieces of you, the smallest pieces of this planet, the smallest pieces of every star you have ever seen, are not really things at all. They are ripples. Ripples in something invisible that fills every cubic inch of space, from the ocean floor to the edge of the observable universe. Physicists call these invisible somethings quantum fields, and the moment you accept they exist, the entire idea of solid matter collapses. Imagine a calm pond stretching forever in every direction. Drop a pebble, a ripple spreads out. That ripple has a shape, a speed, an energy. To a creature living on the surface of the water, the ripple looks like a moving object, but it is not an object. It is a disturbance in the pond. Take the pond away, the ripple cannot exist. Take the ripple away, the pond is still there. Now replace the pond with something far stranger. Replace it with an invisible substance that fills every point of space, including the space inside your lungs, your skull, your cells. Replace the pebble with energy. The ripple that spreads is what we have been calling an electron for a century. Every electron in the universe is a ripple in the same single field. That field has no edge. It does not start somewhere and stop somewhere else. It is everywhere, all at once, all the time. When physicists in Switzerland slam protons together at the Large Hadron Collider and create a new electron, they are not making a thing. They are pinching the electron field hard enough to make it splash. This is the central claim of quantum field theory, the deepest framework physics has ever built, confirmed repeatedly by experiments accurate to 1 part in 10 million. Not a theory in the casual sense, a theory in the sense that it has predicted reality more precisely than any human idea ever has. And it gets stranger. There is not just one field. There is a field for electrons, a separate field for photons, the particles of light, a field for quarks, the things that make up the protons inside your bones, a field for gluons, a field for the Higgs, roughly 17 of them, layered on top of each other, occupying the same space, weaving through every empty room you have ever stood in. You are sitting inside all of them right now. If this sounds like a metaphor, it is not. A team at Cambridge has spent decades writing equations that describe how these fields ripple, interact, and produce the world we measure. Take the fields away, and there is no matter, no light, no gravity, no you. So if reality is not built from particles, what does empty space look like when you really zoom in? The answer is the most disturbing part of the entire story. Place yourself in the deepest vacuum chamber ever built on Earth. The air pressure inside is 1/10 trillionth of the air pressure outside. By every classical definition, the box is empty. There is nothing in it. No molecules, no dust, no light. Look closer. Zoom past anything our microscopes can see. Zoom past the size of an atom, then 1,000 times smaller, then 1,000,000 times smaller. At a certain point, the emptiness starts to boil. This is the quantum vacuum, and it is the most violent place in the universe. Particles are constantly flashing into existence and vanishing again. Pairs of electrons and their mirror twins, the positrons, pairs of quarks. They live for an instant so brief that no clock could ever measure it directly. Then they cancel each other out and disappear back into the field they came from. Physicists call these flickers virtual particles. The vacuum is not nothing. It is a foam. You might wonder how this could possibly be real. The answer comes from a rule called the Heisenberg uncertainty principle. written down in 1927. The principle says you can never know both the energy of a region of space and the exact moment you measured it. There is always a tiny smear, and inside that smear, the universe is allowed to borrow energy from itself, as long as it pays the loan back fast enough. The shorter the loan, the more energy can be borrowed. So in any given speck of vacuum, for an unimaginably small fraction of a second, energy condenses into a pair of particles. Then they collapse, and the books are balanced. Multiply this by every cubic millimeter of space in the universe, every instant, forever, and you start to see what physicists mean when they say the void is alive. This sounds like wild speculation. It is not. We have measured it. In 1948, a Dutch physicist named Hendrik Casimir made a strange prediction. He said that if you place two flat metal plates extremely close together inside a vacuum, the empty space between them should push them toward each other. Not because of gravity, not because of electricity, because the virtual particles outside the plates would have more room to flicker than the virtual particles squeezed between the plates. The pressure outside would be greater. The plates would be shoved together by literal nothing. Decades later, physicists at Los Alamos and Yale built the experiment. They held the plates a few millionths of an inch apart. The plates moved, exactly as predicted. The numbers matched the theory to within 5%. This is now called the Casimir effect, and it is one of the strangest confirmations in modern science. Empty space pushes things around. If you could pull a single grain of sand worth of vacuum out of space and somehow extract its energy, the amount stored inside would be larger than the energy released by every nuclear weapon ever built. We do not know how to extract it. We do not even fully understand why it is there, but it is there. So the universe is built from invisible fields, and even the spaces between them are seething with hidden activity. A reasonable next question follows naturally. If electrons are ripples, what exactly is doing the rippling? For nearly a century, schools taught children that an electron is a tiny particle orbiting the nucleus of an atom, like a planet orbiting the sun. That picture is wrong in almost every way. The orbit is wrong, the shape is wrong, the size is wrong. The very idea of a solid object is wrong. An electron has no measured size at all. Every experiment we have ever done, no matter how powerful, finds the electron to be a point, smaller than 10 to the minus 18 meters across. That is 1/1000th of 1/1000th of a meter. If the electron has any internal structure, our most sensitive instruments cannot find it. Nothing inside, no surface, no edge. Yet the electron has mass, it has electric charge, it carries a property called spin, it interacts with light, it binds itself into atoms. How does something with no size do all of that? The answer is that the electron is not a thing in the usual sense. It is a vibration of the electron field, a single invisible structure that stretches across the entire universe. When that field shakes in a particular pattern, what you measure is one electron. Shake the field somewhere else, you get another electron. Shake it 10 times, you get 10 electrons. They are perfect copies because they are all coming from the same source. This explains a fact that puzzled physicists for decades. Every electron in the universe is identical, not similar, not nearly the same. Identical. The electron in a wire on Earth and an electron in a star, 10 billion light years away, weigh exactly the same, carry exactly the same way. There is no microscopic variation, no manufacturing tolerance, no aging. They are the same because they are not separate objects. They are the same field, shaking in the same way, in different places. Picture a guitar string stretched across all of space. Pluck it here, the string vibrates here. Pluck it on the other side of the galaxy, the string vibrates there. Both vibrations sound exactly the same note because they are the same string. That is what an electron is, a pluck of an infinite cosmic string we cannot see. The same logic holds for every kind of particle. There is one photon field, and every photon ever emitted by every star in the cosmos is a pluck of that single field. There is one upquark field, one Higgs field. The universe contains far fewer ingredients than people imagine. Roughly 17 fields in total, each playing its own song, layered together to produce everything that exists. What we call matter is the music those fields make. Physicists at the Large Hadron Collider in Switzerland confirm this every day. When two protons smash together at nearly the speed of light, the energy of the collision excites the surrounding fields. Those fields ripple, producing showers of new particles that did not exist a moment before. Nothing was hiding inside the protons. The collision simply gave the fields enough energy to vibrate hard enough to make new ripples visible. The deep secret of matter is that there is no matter, only fields, and the patterns they hold for a little while. But fields cannot vibrate without rules. Where did those rules come from, and why does light, of all things, behave so strangely under them? For 200 years, physicists fought a war over the nature of light. Isaac Newton declared it was made of tiny particles, like microscopic bullets fired from the sun. Christian Huygens, his rival across the channel, insisted light was a wave like a ripple on the ocean. Both men were brilliant. Both men had evidence. Both men were partly right and badly wrong. In the early 1800s, an English doctor named Thomas Young settled the argument, or so it seemed. He shone a beam of sunlight through two narrow slits in a card and watched the pattern that landed on a wall behind it. If light were tiny bullets, he should have seen two bright stripes, one for each slit. Instead, he saw stripes of bright and dark bands stacked across the wall. That pattern is the fingerprint of waves. Two wave crests meeting create a brighter spot. A crest meeting a trough cancels out and creates a dark spot. The case was closed. Light was a wave. Then, in 1864, a Scottish physicist named James Clerk Maxwell wrote down 4 equations that explained what kind of wave light actually was. Light, he showed, was a ripple in two interlocked fields, electricity and magnetism, vibrating together at right angles, racing across space at one specific speed. That speed was the speed of light. Maxwell had not just described light, he had unified it with every electric current, every magnet, every spark, into a single phenomenon, the electromagnetic field. For 30 years, this seemed like the final answer. Light was waves in a field. End of story. Then the cracks started to show. A glass tube heated red hot does not just glow. The colors it emits shift in a precise pattern as the temperature climbs. According to Maxwell's wave theory, those colors should have stretched into the ultraviolet without limit, releasing infinite energy. The math predicted that any warm object should burn the universe down. Reality disagreed. Real glass tubes glowed politely, then cooled. This puzzle was called the ultraviolet catastrophe, and it broke physics. In 1900, a German physicist named Max Planck made a desperate move. He suggested that light could only be emitted in tiny chunks, not in a smooth flow. The energy of each chunk depended on its frequency. Higher frequency, bigger chunk. He called the chunks quanta, from the Latin word for quantity. Planck himself thought the idea was a mathematical trick. He did not believe nature actually worked this way. He was wrong. 5 years later, a young patent clerk in Switzerland, named Albert Einstein, took Planck seriously. He used the chunk idea to explain why ultraviolet light could knock electrons out of metal, but red light, no matter how bright, could not. The reason was simple. If you accepted that light came in packets, a red packet did not carry enough energy to dislodge an electron. An ultraviolet packet did. The brightness of the beam only changed how many packets arrived. The packets had to be real. Maxwell's smooth wave theory could not explain it. Light was waves. Light was particles. Light was both, somehow, and neither completely. This was the moment quantum field theory was born, even though nobody yet knew its name. The packets had to be ripples in something deeper than a wave, and the something deeper would soon swallow every other particle in the universe. Bern, Switzerland. 1905. A 26-year-old man sat in an office reviewing patents for clocks and electrical devices. His name was Albert Einstein. His career as a physicist had stalled. He had failed to find a university job. The patent office paid the bills. In his spare evenings, between processing applications, he wrote 4 scientific papers in a single year. Each one alone would have made him famous. Together, they rewired physics. One of them, the one nobody talks about as much as relativity, was about light. The paper was titled, in the language of the time, "On a heuristic viewpoint concerning the production and transformation of light." Heuristic meant a guess. Einstein was being modest. He was about to overturn 2 centuries of consensus. The mystery he attacked was the photoelectric effect. Shine a beam of light onto a clean metal surface inside a vacuum tube, and electrons fly off. That much was known. What baffled scientists was the pattern. A faint ultraviolet light could knock electrons free instantly. A blinding red light, 10,000 times brighter, could not knock loose a single one. No matter how long you waited, no matter how hot you cranked the lamp. This made no sense if light was a wave. A wave delivers energy gradually. Brighter wave, more energy, more electrons knocked loose. The metal did not care. Einstein proposed something heretical. He said light was not really a wave at all, at least not in the way Maxwell had taught. Light came in discrete bullets of energy. Each bullet carried a fixed amount of punch determined by its color. Ultraviolet bullets were strong. Red bullets were weak. A weak bullet, no matter how many of them you fired, could never push an electron out of its atomic socket. A strong bullet could do it on the first hit. The brightness of the beam only counted how many bullets per second, not how powerful each one was. Today we call those bullets photons. They are the particles of light. Each photon is a single ripple in the electromagnetic field, the smallest possible disturbance that field can carry. Einstein won the Nobel Prize for this paper in 1921. The committee specifically chose his work on the photoelectric effect, not relativity, because relativity was still considered too radical to honor officially. The photon was the safer choice. But the photon was anything but safe. It opened a door that physics has never managed to close. If light, the most familiar wave in the universe, was actually made of countable particles, then what about the things we already thought were particles? What about electrons? What about protons? Could a particle be a wave the way a wave could be a particle? A French aristocrat named Louis de Broglie answered the question in 1924 in his doctoral thesis. He proposed that every chunk of matter in the universe also had a wavelength. An electron, a proton, even a baseball was secretly a wave too. The bigger the object, the smaller the wavelength, which is why we never notice the wave nature of a baseball. But for an electron, the wavelength was huge compared to the particle itself. 3 years later, an American team at Bell Labs fired electrons at a nickel crystal and watched them produce the same striped pattern Thomas Young had seen with light a century earlier. Electrons were waves. Everything was waves. Everything was particles. Reality refused to choose. And the framework that finally explained the contradiction was already growing in the heads of 3 physicists, working in 3 different cities, each closing in on the same impossible truth. By the mid-1920s, 3 young physicists had built the theory we now call quantum mechanics. Werner Heisenberg in Göttingen worked with matrices, dense grids of numbers that captured how particles jumped between energy states. Erwin Schrödinger in Zurich wrote a single elegant equation describing the wave behavior of electrons. Paul Dirac in Cambridge stitched the 2 approaches together, proving they were the same theory wearing different clothes. For a few glorious years, it looked like the universe had been solved. Schrödinger's equation predicted the structure of the hydrogen atom with stunning accuracy. It explained why atoms had the colors they did. It explained chemistry. It explained the periodic table. Physicists toasted each other in cafes across Europe. Then someone asked an awkward question: what happens when the electron moves fast? Schrödinger's equation, brilliant as it was, only worked for slow particles. As soon as an electron crept toward the speed of light, the equation gave nonsense answers. Probabilities went negative. Energies became imaginary. The math stopped describing anything real. The problem was that Schrödinger had built his theory using the old rules of Newton, where time and space were separate things, and speed could grow without limit. But Einstein had already proven 20 years earlier that this was a lie. Time slows down when you move fast. Space contracts. Energy and mass are interchangeable. Any theory that ignored these facts would break the moment particles got energetic enough. Quantum mechanics needed a relativistic upgrade. Without one, it could not describe high-speed collisions, radiation, or the inside of an atom struck by a powerful photon. Paul Dirac took on the challenge in 1928. He locked himself in his office and tried to write down a quantum equation that respected Einstein's rules. The math fought him. Every solution he found seemed to require negative energy states, which made no physical sense. Particles cannot have less than zero energy. That would mean they could fall forever, releasing infinite power. Dirac stared at his equations for months. Then he made a wild leap. He suggested that the negative energy states were real, but they were already filled. Every spot in space contained an invisible sea of negative energy electrons, packed shoulder to shoulder, hidden because they were everywhere. We could not see the sea any more than a fish can see water. Only when something punched a hole in it, freeing one of the negative electrons, would we notice. The hole would behave like a particle with positive charge and the same mass as an electron. That hole, Dirac realized in 1931, would be a brand new kind of matter, antimatter. A year later, a physicist named Carl Anderson photographed a strange track in a cloud chamber in California, a particle with the mass of an electron but bending in the opposite direction in a magnetic field. He had found Dirac's hole. He named it the positron, the mirror twin of the electron. Dirac's equation was right, but the price was steep. To make quantum theory and relativity get along, the universe had to be filled with hidden particles. The simple picture of a single electron orbiting an atom was already dying. Every particle now came with a partner. Every space was already occupied. Quantum mechanics had grown up. It needed something bigger to live inside. That something would not be an equation. It would be an entire new picture of reality. Two of the most successful theories in human history did not get along. Quantum mechanics described the behavior of the very small, the world of atoms, electrons, and photons. Special relativity described the behavior of the very fast, the world of light beams, racing rockets, and energy turning into matter. Each theory worked perfectly inside its own kingdom, crossed the border between them, and both collapsed. Quantum mechanics assumed time was a steady background ticker, the same for everyone. Relativity proved that time stretched and squashed depending on how fast you moved. Quantum mechanics treated particles as fixed objects that could be tracked from one moment to the next. Relativity allowed particles to be created from pure energy and destroyed back into pure energy, following the famous formula relating energy and mass. The two theories used different definitions of reality. For most of the 1930s, this mismatch felt like a technical inconvenience. Physicists patched it up with clever tricks. Then the cracks widened. Consider what happens when an electron emits a photon. According to relativity, the energy of the photon comes from the kinetic energy of the electron. Mass and energy can flow into each other. So in any high-energy interaction, particles can appear and disappear. The number of objects in a box is not fixed. It changes from moment to moment as energy gets redistributed. But quantum mechanics, in its original form, had no way to handle this. Schrödinger's equation tracked exactly one electron, or exactly two, or exactly five. It could not gracefully describe a situation where an electron suddenly turned into an electron plus a photon plus another electron-positron pair, with all of them flickering in and out of existence. The fix arrived in the late 1940s after a long pause caused by the Second World War. Three physicists, working independently, cracked the problem. Richard Feynman in the United States approached it with a wild new visual method, drawing little diagrams of arrows and squiggles that represented all the possible paths a particle could take. Julian Schwinger, also American, attacked it with austere mathematics so elegant that almost nobody could understand him. Sin Ichiro Tomonaga in war ravaged Japan, working with rationed paper and broken laboratory equipment, arrived at essentially the same answer through a third route. All three were doing the same thing. They were promoting fields, not particles, to be the fundamental objects of nature. In their new framework, called quantum electrodynamics, the electromagnetic field was the real thing. Photons were not separate objects. They were excitations of the field. Electrons were excitations of a different field. The two fields were tangled together by mathematical rules that respected both quantum uncertainty and Einstein's relativity at the same time. When an electron emitted a photon, the electron field rippled, its energy dropped slightly, and the electromagnetic field gained a corresponding ripple. Energy was conserved, relativity was respected, quantum strangeness was preserved. The theory made predictions of staggering precision. The magnetic strength of an electron, for example, could be calculated to within one part in a trillion. When physicists measured it in the lab, the number agreed exactly. No human theory had ever been so accurate about anything. Feynman, Schwinger, and Tomonaga shared the Nobel Prize in 1965. Quantum field theory was born, and it changed what physicists meant by the word reality. The next puzzle was bigger than electrons and photons. If matter was made of fields, how many fields were there, and what were they? Once physicists accepted that the electron came from a field and the photon came from a field, they started looking for more. Every type of particle they discovered turned out to have its own field underneath it, like a hidden instrument backing a single note in an orchestra. By the late 20th century, the count had settled at roughly 17. Each one fills the entire universe. Each one occupies the same space as all the others. They overlap, they pass through each other, they push and pull on each other through interaction rules written in deep mathematics. Standing in your kitchen right now, you are inside 17 invisible oceans at once. The first group is the matter fields. 6 are quark fields, named with quirky labels physicists picked half as a joke. Up, down, charm, strange, top, bottom. Each one is a different kind of building block for the heavy particles inside atoms. The proton in your hand is made of 2 ripples in the up quark field and 1 ripple in the down quark field, locked together. The neutron next to it is 2 down ripples and 1 up ripple. Every single proton in every star in the visible universe is built from the same up and down quark fields. There is no other source. Then there are the lepton fields. 6 again: the electron field, the muon field, the tau field, and 3 corresponding fields for the strange quiet particles called neutrinos: electron neutrinos, muon neutrinos, tau neutrinos. Trillions of them are passing through your body every second, ripples in their fields so faint they barely interact with anything. They were born inside the sun 8 minutes ago, and now they are streaming through the Earth as if it were not there. That brings the matter count to 12 fields, 6 quarks, 6 leptons. Together they form everything you have ever touched, eaten, breathed, or loved. Then come the force fields. The photon field carries electromagnetism, which holds your atoms together, makes light, creates magnetism, and runs every electronic device. The gluon field carries the strong force, which glues quarks together inside protons. There is not just one gluon. There are 8 different ways the field can ripple, like 8 strings on a single instrument. Then the W and Z fields handle the weak force, which controls certain types of radioactive decay and is the reason the sun shines. That makes 16. The last one is the most mysterious, the Higgs field. Unlike the others, the Higgs field does not have to ripple to be present. It has a permanent value at every point in space, a constant background hum. Ripples in this field appear as Higgs bosons, the famous particles confirmed at the Large Hadron Collider in 2012. But the field itself is more important than its ripples. It is what gives most of the other fields the property of mass. 17 fields, layered into the same volume of space. That is the entire ingredient list of the universe, according to current physics. Everything you have ever experienced is some combination of vibrations across this set. The list is small, almost embarrassingly small for something as vast as a cosmos. Physicists still wonder if it is the final list, or if there are more fields hiding behind dark matter and dark energy, waiting to be found. But if the universe is layered with these endless fields, what is happening in the gaps between their ripples? The answer is something that should not exist at all. When physicists talk about empty space, they do not mean what most people mean. To a physicist, empty space is a region of every quantum field set to its lowest possible state. No real particles, no light, no matter, just the fields themselves, sitting at rest. But sitting at rest in quantum theory is not the same as sitting still. A field at its lowest state still trembles. It cannot help it. The Heisenberg uncertainty principle forbids any field from being perfectly motionless, just as it forbids a particle from having both a perfectly known position and a perfectly known speed. The minimum amount of motion is built into the rules of nature. Take it away, and the universe stops working. This trembling produces something extraordinary. Pairs of particles flicker into existence and vanish back into the field, faster than any clock can catch them. An electron and a positron appear. They live for a nearly non-existent slice of a second. They annihilate each other. The energy is returned to the field. The vacuum looks unchanged. Physicists call these flickers virtual particles. The name is technical, not casual. They are real in the sense that they affect the world. They are virtual in the sense that they cannot be caught directly with a detector. They are the bookkeeping the universe does when it is allowed to break the rules briefly, as long as it puts everything back before anyone notices. If this sounds invented, consider how physicists use it. Every calculation in modern particle physics, including the calculations that designed the chips inside your phone, depends on virtual particles. When two electrons repel each other, the force does not travel between them as some abstract field line. It travels as virtual photons popping out of the electromagnetic field, crossing the gap, and being reabsorbed by the other electron. Multiply this by every charged particle in your body, and you understand why the floor holds you up. Virtual photons are doing it. Virtual particles also explain something even stranger. Around any real particle, there is a thin haze of virtual particles constantly forming and dissolving. An electron sitting in space is not really alone. It is surrounded by a fizzing cloud of virtual photons, virtual electron-positron pairs, virtual everything. This cloud actually changes the measured properties of the electron itself. Its mass, its charge, its magnetic strength, all get tweaked by the influence of the cloud. Physicists at Harvard measured the magnetic moment of the electron in 2008. Their answer matched the quantum field theory prediction, including the cloud of virtual particles, to 1 part in a trillion. The cloud is real enough to be measured. There is an even wilder consequence. Inside the cloud surrounding a heavy particle, virtual particles can briefly become real. If the original particle is unstable, like a uranium nucleus, the constant fluctuation can trigger an actual decay. The radioactive clicks counted by a Geiger counter at a hospital are produced by virtual particles momentarily becoming real and pushing the system over the edge. The vacuum, then, is not empty. It is a furnace of probability, constantly producing and destroying matter at scales too small for our instruments to resolve. Stop it, and physics breaks. Allow it, and the universe runs. But this raises an obvious test. If virtual particles are real, they should produce a force we can measure directly. Not a calculation correction, not a tweak. An actual physical push, large enough to move metal plates we can see with our eyes. 2 Dutch physicists predicted exactly that in 1948. And when their prediction was finally tested, the result was even stranger than they expected. In 1948, the Philips Research Lab in the Netherlands was racing to understand why fluids flowed strangely between certain materials. A theoretical physicist there named Hendrik Casimir was assigned to figure out the cause. While working through the math, he noticed something that had nothing to do with the original problem and everything to do with the structure of empty space. Casimir realized that if you placed 2 flat metal plates extremely close together inside a vacuum, the virtual particles of the electromagnetic field would behave differently inside the gap than outside it. Outside the plates, the virtual photons could ripple at any wavelength they liked, with no restrictions. Inside the gap, only certain wavelengths fit, the same way only certain notes can fit between 2 walls in a guitar. This meant the virtual photon population outside the plates was richer than the population inside. More fluctuations outside, fewer inside. The pressure from the bigger crowd outside would push the 2 plates together. Empty space itself would shove them. Casimir worked out the formula. The force was tiny, but real. For 2 plates placed about 1 micron apart, roughly 1/40th the width of a human hair, the inward push would be about 1/1000th of the weight of a fly. Small, but measurable. For decades, nobody could measure it. The plates had to be perfectly flat, perfectly clean, and perfectly parallel, sitting in a chamber with almost no air. Any speck of dust would ruin the experiment. Any vibration from a passing truck would scramble the result. In 1997, an American physicist named Steve Lamoureux at the University of Washington finally pulled it off. He used a sensitive torsion pendulum and a curved metal lens placed near a flat plate, both coated in gold. He cooled the system, isolated it from vibration, and slowly brought the surfaces close together. The plates moved. The force matched Casimir's prediction to within 5%. A year later, a team at Bell Labs improved the precision to within 1%. The Casimir effect was confirmed. Empty space was pushing real metal around. Think about what this means. There is no air between the plates, no light, no matter. By every classical definition, there is nothing in the gap. Yet the gap pushes back. The only thing in there is the absence of certain kinds of vacuum fluctuation, and that absence is enough to generate a real force you can read off a meter. The implications spread outward. Engineers at MEMS laboratories now have to design tiny machines, smaller than a pinhead, that account for the Casimir force pulling their components together. If they ignore it, the moving parts of microscopic devices stick to each other and lock up. The vacuum becomes a real engineering problem. A team in Sweden took the experiment further in 2011. Instead of holding the plates still, they vibrated one of them at a frequency close to the speed of light, billions of times per second. The vibrating mirror could not keep up with the virtual photons. Some of those virtual photons got separated from their partners and turned into real photons, which the team detected as light streaming out of a region that had been completely dark. They had created light from nothing, not from energy stored in a battery, from the structure of the vacuum itself. Empty space turned out to be the most active substance in the universe, and the rule that makes it boil is the same rule that decides what we are even allowed to know. The engine driving every quantum field is a single principle written down in 1927 by a 25-year-old German physicist named Werner Heisenberg. It is called the uncertainty principle, and it is the most misunderstood idea in modern physics. Most people hear the name and think it is about measurement. They picture a clumsy scientist disturbing a particle by trying to look at it, and they assume the uncertainty principle says we cannot know everything because our tools are not good enough. That is wrong. The uncertainty principle is not about our tools, it is about reality. Heisenberg proved that for any pair of certain physical quantities, like the position and the speed of a particle, the universe itself does not allow both to be perfectly defined at the same time. It is not that we cannot measure them, it is that the particle does not have them. Push the position into sharp focus, and the speed becomes a smear of possibilities. Pin down the speed, and the position blurs out. This rule extends to other pairs too. Energy and time. The exact energy of a system cannot be known precisely if you only watch it for a short window. The shorter the window, the bigger the possible energy fluctuation. In a long enough window, energy is conserved exactly. In a brief enough window, energy can wobble freely without breaking any law. This is the loophole that makes virtual particles possible. The vacuum is allowed to borrow energy as long as the borrowing happens fast enough. Borrow more, return faster. Borrow less, hold longer. The cosmic accountant balances the books, but the books are blurry inside the smallest moments. Heisenberg derived this from the basic mathematics of waves. If you take any wave and try to localize it, squeezing it into a tiny region of space, you have to add together waves of many different wavelengths to make the squeeze work. More wavelengths mean a wider spread of possible momenta. The same trick works in reverse. A wave with a single sharp wavelength has to spread out across all of space. Particles, as ripples in fields, follow the exact same rule. A ripple with a sharply defined location must have a fuzzy momentum. A ripple with a sharp momentum must be spread out across a huge volume. This explains a fact that bothered physicists for decades. Why do atoms not collapse? In the old picture of an atom, an electron orbits a nucleus the way a planet orbits a star. According to classical physics, that electron should radiate energy as it accelerates around the curve, spiral inward, and crash into the nucleus within a fraction of a second. But atoms do not crash. Hydrogen has been hydrogen for 14 billion years. The uncertainty principle saves them. If an electron tried to sit at the center of the nucleus, its position would be sharply defined, which means its momentum would have to be enormous. It would jet out at near light speed. The minimum possible energy of an electron near a nucleus is set by the balance between these two demands. At a certain distance, the electron settles. It cannot get any closer without violating the rule. That distance defines the size of the atom. Without the uncertainty principle, every atom in the universe would collapse instantly into a blob smaller than a particle. There would be no chemistry, no biology, no you. The trembling of the quantum vacuum, the boiling of virtual particles, the size of every atom, all flow from the same simple fact. Stillness is forbidden. But that fact has a deeper consequence, one that physicists are only now beginning to take seriously. In 1940, a young Princeton physicist named John Wheeler picked up the phone late at night and called his student, Richard Feynman. Wheeler was breathless. He thought he had cracked one of the strangest puzzles in physics. Why, he asked, are all electrons identical? Every electron in every atom in every galaxy weighs exactly the same. It carries the same negative charge. It spins the same way. There is no microscopic deviation, no manufacturing tolerance, no aging. An electron made yesterday at the bottom of a particle accelerator in Geneva is indistinguishable from an electron in a star at the edge of the visible universe. Wheeler had a wild theory. What if there is only one electron? A single electron traveling forward and backward in time, weaving through the entire history of the universe so many trillions of times that it appears in every atom, on every world, simultaneously. Each crossing of its path looks like a separate electron to us, but it is all the same particle, going around and around through time. Feynman never fully accepted the idea, but Wheeler's wild guess pointed at something real. The reason electrons are identical is connected to something deeper than coincidence. They are the same because they come from the same field. Quantum field theory delivers a much cleaner answer than time loops. Every electron in the universe is a ripple in the electron field, and that field is one single object spanning all of space. The field has fixed properties. When it ripples into the pattern that we recognize as a particle, that pattern always has the same mass, the same charge, the same spin. The field is the master copy. Every electron is a printout from it. The same logic applies to every other type of particle. All protons in your body have the same mass as all protons in Andromeda. All photons of a given color carry the exact same energy. There is no spectrum of slight differences. The universe is mass-produced from a finite list of perfect templates. This is a surprisingly profound fact. In a non-quantum world, you would expect identical particles to be a coincidence at best. 2 billiard balls might look the same, but if you weighed them on a sensitive enough scale, you would find tiny differences. Real objects vary, manufacturing is imperfect, but fundamental particles do not vary at all. Down to the limits of our measuring instruments, the variation is exactly zero. It also explains a strange behavior physicists call indistinguishability. When two electrons collide and bounce off each other, you cannot tell which one came out the left side and which one came out the right side. They are interchangeable in a way no 2 billiard balls ever are. If you swap two electrons in a calculation, the answer does not change. They are mathematically the same object in two locations. This indistinguishability has real, measurable consequences. It is the reason atoms have shells. The reason no two electrons in the same atom can occupy the same quantum state. The reason chemistry has periods and groups instead of every atom looking like every other atom. A rule called the Pauli exclusion principle forces identical electrons to keep their distance, and that rule only works because they are truly identical to begin with. Take away the field picture, and this all becomes magic. Why should two unrelated particles be perfectly the same? Why should they obey rules that depend on their interchangeability? The field picture answers both questions in the same breath. There are not two particles. There is one field vibrating twice. But there is one special field that does something the others do not. It is the reason any of these particles have weight at all. For decades, physicists building the standard model of particles ran into a stubborn obstacle. The math worked beautifully if every particle in their equations was massless. As soon as they tried to give the particles weight, the equations broke. Predictions exploded into infinities. The theory collapsed. This was a problem because particles obviously have mass. An electron weighs about 9 times 10 to the minus 31 kilograms. A proton weighs about 1,800 times more. A top quark is almost 200,000 times heavier than the electron. Mass is real, measurable, and varies wildly between different types of particles. Yet the cleanest version of the theory wanted them all to be weightless. The fix was proposed in 1964, almost simultaneously, by 3 independent groups: Robert Brout and François Englert in Belgium, Peter Higgs in Scotland, Gerald Guralnick, Carl Hagen, and Tom Kibble at Imperial College London. They all reached the same idea, with slight variations. They suggested that an additional field existed, filling all of space with a constant non-zero value, even at the lowest possible energy. Most fields, when undisturbed, sit at zero. This new field never sat at zero. It always had a background hum, the same in every cubic millimeter of the universe. Particles moving through this field would interact with it. The strength of their interaction would determine the mass we measure for them. The field is now called the Higgs field, named after Peter Higgs, partly because his paper was the clearest in describing how the corresponding particle would behave. The story is a little unfair to the others, but the name stuck. Most popular descriptions of the Higgs field compare it to a thick liquid that drags on particles, slowing them down. Physicists hate this analogy because it is wrong. A drag force would slow particles continuously, and yet electrons in a vacuum keep moving at constant speed forever. The Higgs field does not drag. It does something subtler. Here is the better picture. Imagine each kind of field as a guitar string. A particle is what you get when the string vibrates at a particular frequency. Most fields can vibrate at any frequency, including zero. A field vibrating at zero produces a massless particle, like a photon. The Higgs field interferes with other fields by stiffening them. A stiffened field cannot vibrate slowly. It has a minimum vibration rate built in. That minimum vibration rate is what we call the rest mass of a particle. The more strongly a particle field couples to the Higgs field, the more it gets stiffened, the higher its minimum frequency, the larger its mass. The top quark interacts with the Higgs strongly, so it is heavy. The electron interacts weakly, so it is light. The photon does not interact with the Higgs at all, so it is massless and travels at light speed. For nearly 50 years, the Higgs field was a theoretical idea. Physicists had no direct way to test whether the field actually existed. They could only see its consequences, and those consequences might have come from something else. The proof would have to come from making the field ripple. Hit it hard enough, and it should produce a single particle, the Higgs boson. Find that particle, and the field would be confirmed. Fail to find it, and the entire standard model would collapse. The hunt would take half a century, the largest machine ever built by human beings, and a moment of confirmation that left the world's best physicists in tears. In a tunnel beneath the border between France and Switzerland, 17 miles long and 300 feet underground, sits the Large Hadron Collider. It is the most complex machine humanity has ever built. Inside, two beams of protons race in opposite directions through a vacuum colder than outer space, kept on track by superconducting magnets, cooled to a temperature near absolute zero. The protons travel at more than 99.999% of the speed of light, completing the full ring 11,000 times every second. The whole apparatus exists to do one thing: smash protons together hard enough to make the Higgs field ripple. The reason this is so difficult comes down to energy. The Higgs boson, the particle that appears when the Higgs field vibrates, weighs about 125 times as much as a proton. To create it, you have to deliver that much energy into a single point in space. Then, even when you succeed, the Higgs boson decays in less than 1/billionth of 1/trillionth of a second, far too fast to detect directly. Physicists can only see the shower of secondary particles it produces as it falls apart. The hunt began in earnest in the 1980s. Earlier accelerators in Europe and the United States searched for the Higgs at lower energies and found nothing. The Tevatron at Fermilab in Illinois pushed harder through the 1990s and the early 2000s. Still nothing. The Higgs, if it existed, was hiding above the energy range those machines could reach. The Large Hadron Collider was designed specifically to close the gap. Construction began in 1998. It cost more than $9 billion. 20,000 scientists from over 100 countries collaborated on the two main detectors, called Atlas and CMS, each one the size of a cathedral, packed with millions of sensors capable of tracking particle paths to within a few millionths of a meter. The machine started running in 2009. 3 years of collisions followed. Trillions upon trillions of proton smashes were recorded. Computers sifted through the data, searching for the rare statistical bumps that would signal a Higgs decay against the background noise. On the morning of July 4, 2012, the directors of the Atlas and CMS experiments stood in front of an audience at CERN headquarters. Peter Higgs himself, 83 years old, sat in the front row. The lead physicist of CMS, a woman named Jo Incandela, walked through the data slide by slide. The room saw a clear bump at 125 giga-electron volts. The Atlas team showed the same bump in their independent data. The signal had a statistical significance of 5 sigma, the formal threshold for discovery in physics. The probability that the bump was a coincidence was about 1 in 3.5 million. Peter Higgs took off his glasses and wiped his eyes. He had waited 48 years to see his prediction confirmed. The Higgs boson was real. The Higgs field was real. The mechanism that gives mass to every electron, quark, and weighty particle in the universe was no longer theory. It was measurement. A year later, Peter Higgs and Francois Englert shared the Nobel Prize in Physics. Robert Brout had died in 2011, 8 months too soon to receive the honor. But the discovery raised an even stranger question. If the Higgs gives mass to particles by stiffening their fields, why does the photon get nothing while the electron gets a little and the top quark gets enormous amounts? Of all the elementary particles in the Standard Model, the photon is the only one with no mass at all. It carries energy, it carries momentum. It can knock electrons out of metal, but it has no rest mass. Place a photon at rest, and it ceases to exist. Photons are condemned to travel at the speed of light forever, never slowing, never settling. The electron, by contrast, has a small but definite mass. The top quark, the heaviest known elementary particle, weighs nearly 200,000 times as much as the electron. A muon, which is just like an electron in every other way, weighs more than 200 times as much. Why this scattershot range? The answer hides in how each particle field interacts with the Higgs field. Some fields couple to the Higgs strongly, some do not couple at all. The strength of the coupling sets the mass. Picture the Higgs field as a fog filling all of space. Different fields move through this fog with different sensitivities. The photon field is completely transparent to the fog. It does not feel the Higgs at all. So a photon, when it appears as a ripple in its field, has nothing slowing its lowest possible vibration. It can vibrate at any frequency, including zero. A zero-frequency vibration corresponds to zero mass. The photon ends up weightless and forever in motion. The electron field interacts with the Higgs fog weakly. The interaction is enough to stiffen the electron field slightly. Its lowest possible vibration is no longer zero. It has a small minimum frequency. That minimum frequency is the electron's rest mass. The top quark field interacts with the Higgs fog ferociously. The Higgs grabs onto the top quark field hard, raising its minimum vibration frequency to an enormous value. That is why the top quark is so heavy. The fog drags violently on it. The muon and the tau, both heavier cousins of the electron, sit between these extremes. They share the same overall structure as the electron, but have different coupling strengths to the Higgs. Why those coupling strengths take exactly the values they do is one of the great unsolved questions in physics. The Standard Model can predict everything else once you plug in the coupling constants, but it cannot predict the constants themselves. They have to be measured and entered by hand. Physicists call this the hierarchy problem in part, and it is one of the reasons some researchers suspect there must be more to the Standard Model than what we currently see. The pattern of masses, ranging across a factor of 200,000 among the matter particles, looks too uneven to be accidental, yet no deeper reason for it has been found. There is one more twist. Most of the mass in the everyday world does not come from the Higgs at all. The proton in your hand has a mass nearly 1,800 times the electrons, but the 3 quarks inside the proton, when their individual Higgs masses are added up, account for only about 1% of the proton's total weight. The remaining 99% comes from the energy of the strong force binding the quarks together. Mass and energy are interchangeable, and inside a proton, almost all of what you weigh is locked up energy. Your body is mostly bound energy held together by the strong force, with a tiny dusting of Higgs-derived mass on top. Without the Higgs, the dust is gone, and atoms cannot form. Without the strong force binding, the protons fall apart. Both are required. But the Higgs field has another secret. It did not always have its current value. There was a time, very long ago, when it was zero everywhere, and the universe looked nothing like today. For the first tiny fraction of a second after the Big Bang, The universe was hotter than anything we can describe with familiar comparisons. Temperatures climbed past 1,000,000,000 degrees. At those energies, the Higgs field had no preferred value. It sat at zero everywhere. Nothing had mass. Every particle was massless and moved at the speed of light. The four forces of nature, which today look completely different, were unified into a single unified force. There was no chemistry, no atoms, no structure, just a violent uniform soup of massless ripples flying in every direction. As the universe expanded, it cooled. Within the first picosecond, the temperature dropped enough that the Higgs field could no longer maintain its zero value. Like supercooled water suddenly freezing, the field snapped to a new equilibrium. Across the entire cosmos, the Higgs field locked into a constant non-zero value, the same value it still holds today. This event is called electroweak symmetry breaking. The instant it happened, particles got mass. The fields that had been swimming freely through the previous emptiness suddenly stiffened. The W and Z bosons, which carry the weak nuclear force, gained huge masses overnight. The electron field gained its small mass. The quark fields gained their various masses. Only the photon field, which never coupled to the Higgs, kept its original massless state. The four forces split apart. What had been a single unified force shattered into electromagnetism, the weak force, the strong force, and gravity. They now look entirely different from each other, but in the very early universe, they were the same thing. This is why physicists often call the Standard Model the result of a frozen accident. The universe cooled, the Higgs field picked a value, and everything we now experience flows from that frozen choice. If the Higgs had locked into a different value, particle masses would be different. Atoms might not form. Stars might not exist. We might not be here. There is no agreed reason why the Higgs picked the value it did. It might be the only stable choice. It might be one of many possible choices, with our universe just happening to land on this one. There are physicists who argue, half seriously, that what we call the laws of nature are not laws at all. They are local conditions set by the way the fields happened to freeze when the universe was a fraction of a second old. The math behind symmetry breaking is borrowed directly from condensed matter physics. The same math describes how a hot iron bar, cooled below a critical temperature, suddenly becomes magnetic. Above the critical temperature, the iron atoms point in random directions. Below it, they all line up. Nobody told them which way to align. They just picked a direction together, breaking the symmetry of the system. The universe did the same thing on a cosmic scale. The Higgs field, faced with cooling, picked a direction. Once it picked, it held that direction across all of space. What would happen if it ever changed its mind? What if some local region of space found a slightly more stable Higgs value and snapped to it? The change would spread outward at the speed of light, rewriting the rules of physics as it went. Atoms in its path would dissolve, stars would lose their structure, everything we know would be replaced by something different in the bubble. Physicists call this scenario vacuum decay. Most calculations suggest the current Higgs value is stable enough to last far longer than the current age of the universe. Most, not all. There are versions of the math that say we are sitting on a metastable knife edge, waiting for the right random fluctuation to push us over. But before we trace that doomsday possibility, there is another field doing strange things inside every proton in your body, and it works in a way that violates almost every intuition about how forces should behave. Every other force in the universe gets weaker as you pull objects apart. Gravity fades with distance. Electromagnetism fades with distance. Move two magnets far enough away from each other, and they stop attracting. Move two charged particles apart, and the repulsion drops off. The strong force does the opposite. Try to pull two quarks apart inside a proton, and the force pulling them back grows stronger the farther you separate them. Pull harder, and the bond tightens. There is no escape. The force does not give up. This bizarre behavior is the signature of the strong nuclear force, mediated by particles called gluons, ripples in a field called the gluon field. It is the force that holds quarks together inside protons and neutrons, and it is what locks protons and neutrons together to form atomic nuclei. Without it, no atom heavier than hydrogen could exist. Your body would not assemble. Stars could not fuse hydrogen into helium. The universe would be a thin, lifeless gas. Quarks come in three-color charges: an unfortunate name since they have nothing to do with visible color. Physicists labeled them red, green, and blue, but the labels just stand in for three different mathematical states. A proton contains three quarks, one of each color, which combine to make a colorless object, the way mixing red, green, and blue light produces white. The strong force only allows colorless combinations to exist as free particles. Anything carrying a net color charge is immediately bound to other quarks until the colors cancel out. Gluons are the messenger particles of the strong force. Unlike photons, which carry no charge themselves, gluons carry color charge. This is the weird part. A photon does not feel the electromagnetic force directly. It only carries the message between charged objects. A gluon, by contrast, feels the strong force itself. Gluons interact with other gluons. They tangle together, they pull on each other. This self-interaction is why the strong force grows with distance. When you try to pull two quarks apart, gluons stretch between them like a rubber band. As the band stretches, it does not weaken. It tightens. More gluons are produced from the energy you are pumping in. The band gets thicker, not thinner. Pull hard enough, and the rubber band has so much energy stored in it that the energy spontaneously turns into a new pair of quarks. The band snaps in the middle, and where you used to have two separated quarks, you now have two new pairs of quarks, each one bound up. You cannot ever isolate a single quark. The math forbids it. Any attempt to extract one creates new ones to keep it company. This phenomenon is called color confinement, and it has been confirmed by every high-energy collision experiment ever performed. No one has ever detected a free quark drifting through space. Quarks only exist inside the cages built from the gluon field around them. The same gluon energy that confines quarks is also where most of the mass in your body comes from. Earlier we noted that the Higgs field accounts for only about 1% of the proton's mass. The other 99% is the energy stored in the gluon field, locked between the three quarks inside, churning constantly, holding everything together. You are heavy not because you are full of stuff. You are heavy because you are full of trapped energy. The strong force is also the reason the sun shines, the reason elements heavier than hydrogen exist, and the reason Earth contains anything at all besides primordial gas. But there is a fourth force, the strangest of all, the one that turns one particle into another, and it controls something far more intimate than nuclear fusion. Picture trying to lift a single brick out of a wall, only to find that the harder you pull, the more bricks materialize in your hand. That is what happens every time a physicist tries to extract a lone quark from a proton. The universe simply refuses to let it happen. Quarks are the only known type of matter particle that nobody has ever isolated, photographed, or held still on its own. This rule has a name: color confinement. It says that any particle carrying color charge must always be bound up with others into a colorless combination. Three quarks together work. A quark paired with an antiquark works. A single quark on its own does not. The math of the gluon field literally prohibits it. When physicists at the Stanford Linear Accelerator first probed inside protons in 1968, they fired electrons into hydrogen atoms at extremely high energy. The electrons bounced off something hard inside the proton, sharp little kernels. The team called them partons at first, not yet ready to commit to the name quark. The kernels behaved strangely. At very short distances they seemed almost free, drifting around inside the proton with little resistance. At larger distances, they became impossible to pull apart. This counterintuitive feature was named asymptotic freedom. Inside a proton, when two quarks are extremely close together, the strong force between them is weak. They jiggle around almost as if no bond existed, move them apart by even the tiniest amount, and the bond clamps down. Three physicists, David Gross, Frank Wilczek, and David Politzer, worked out the math behind this in 1973. They received the Nobel Prize for it in 2004. The quarks inside you have never been alone. Every up quark in your body has been paired with two others since the universe was less than a microsecond old. The down quarks are the same. They formed in the cooling plasma after the Big Bang and have remained locked together ever since. Physicists can briefly create conditions in which quarks roam more freely. At the relativistic heavy ion collider on Long Island, researchers smash gold nuclei together at near light speed. The collision releases so much energy that the protons and neutrons inside the nuclei melt, turning into a soupy substance called quark-gluon plasma. In this state, which lasts for roughly 1/10,000th of 1/trillionth of a second, quarks can move past each other without being trapped in groups of 3. The plasma is hotter than anything in the natural universe today, around 4 trillion degrees. Hotter than the core of any star, the plasma cools instantly back into ordinary protons and neutrons. The quarks lock up again. This was the state of the entire universe for about 10 microseconds after the Big Bang. Every quark and gluon you contained spent that brief era as part of the cosmic soup before the temperature dropped enough for confinement to take hold. Inside a single proton, the picture is even stranger than 3 quarks holding hands. The 3 valence quarks, the ones that give the proton its charge and most of its identity, are surrounded by a roiling sea of virtual quarks and antiquarks constantly appearing and disappearing. Gluons fill the space between them, also flickering in and out of existence. The proton is not 3 little balls. It is a churning storm of fields, and the 3 quarks are the parts that happen to stay around. What you experience as solid matter is a structure built on chaos that never stops. But there is a force inside you doing something even more invasive. It changes one kind of particle into another, and it powers the engine of every star you have ever seen. Inside the core of the Sun, every second, 600 million tons of hydrogen fuse into helium. Of all the energy released in that process, a tiny fraction comes from a strange kind of physics that has no parallel in everyday experience. It is the only force capable of changing one type of particle into a completely different type. Physicists call it the weak nuclear force, and despite its modest name, it controls life and death across the cosmos. The weak force has its own field, and like every other force in the Standard Model, it has its own messenger particles. There are 3 of them. 2 are called the W bosons, one positively charged and one negatively charged. The third is called the Z boson, which is electrically neutral. Together they ripple through what is called the weak field, which fills all of space alongside every other quantum field. What makes the weak force unique is its ability to flip particles into different identities. When a neutron decays inside an unstable atom, one of its down quarks emits a W boson and turns into an up quark. The neutron, which is made of 2 down quarks and 1 up quark, becomes a proton made of 2 up quarks and 1 down quark. The W boson immediately decays into an electron and a tiny neutrino. From outside, it looks like the neutron simply spat out an electron and changed its identity. That radioactive emission is called beta decay, and it is the reason carbon dating works, the reason nuclear reactors generate electricity, and the reason certain medical scans can detect cancer. Without the weak force, the sun would not shine. The first step in solar fusion requires 2 protons to slam into each other and merge. But 2 protons cannot stick together by the strong force alone, because both carry positive charge and repel each other electrically. The merger only succeeds when one of the protons converts into a neutron during the collision, mediated by the weak force. The new proton plus neutron pair forms a deuterium nucleus, and from there, the fusion chain proceeds toward helium. The sun runs because the weak force lets protons change identity. The reason the weak force is called weak is that its messenger particles are extraordinarily heavy. The W and Z bosons each weigh about 100 times as much as a proton. Heavy messengers cannot travel far before they decay back into other things. The range of the weak force is therefore tiny, less than 1,000th the diameter of a proton. Up close, inside a nucleus, the force can act. Outside, it cannot reach. This is also why the weak force is so much weaker than electromagnetism in everyday life. Photons are massless, so they can travel any distance. They can shape your eyesight and your radio signals. The W and Z bosons have to borrow energy from the vacuum, just to exist for the fleeting moment they need to deliver their message. Heisenberg's uncertainty principle allows this borrowing, but only for an instant. The weak force also has a peculiar property nobody expected. It violates a rule called parity. Most forces work the same way if you flip the universe in a mirror. Gravity does not care which side is left and which is right. Electromagnetism does not care. The strong force does not care. The weak force absolutely cares. It treats left-handed particles differently from right-handed particles. In 1956, two physicists named Sungdao Li and Chen-Ning Yang predicted this, and a year later Qian-Sheng Wu confirmed it experimentally with cobalt-60 atoms. The universe, at the smallest level, is not symmetric. That asymmetry shows up in every star, every nuclear reaction, every breath you take, and it leads to a deeper imbalance, the one that allowed matter to exist in the first place. Every quantum field in the Standard Model has a built-in twin. For every type of matter particle, there is an antimatter counterpart with opposite charge but identical mass. The electron has the positron, the proton has the antiproton, the up quark has the anti-up quark. They are not separate fields. They emerge from the same field, vibrating in mirror image patterns. When Paul Dirac wrote his relativistic equation for the electron in 1928, antimatter fell out of the math whether he wanted it or not. The equation had two sets of solutions, one describing electrons, the other describing something with the same mass but opposite electric charge. Dirac was stunned. He spent 2 years trying to reinterpret the second solution as the proton, since protons were the only positively charged particles known at the time. But the math was clear. The second solution had to have the same mass as the electron, which the proton did not. In 1932, Carl Anderson photographed an unmistakable track in his cloud chamber at Caltech, a particle as light as an electron, curving in a magnetic field in the direction opposite to electrons. He had captured the positron exactly as Dirac's equation predicted. Antimatter was real. When a particle meets its antiparticle, they annihilate. The combined mass converts into pure energy, usually in the form of two high-energy photons flying away in opposite directions. Conversely, if you concentrate enough energy into a small enough region, you can create particle-antiparticle pairs out of seemingly nothing. The fields convert energy into matter and matter back into energy, with perfect balance. This is not a curiosity, it is industrial reality. Hospitals around the world use a technology called positron emission tomography or PET scanning. A radioactive tracer is injected into a patient. As the tracer decays, it emits positrons. Those positrons immediately collide with electrons in nearby tissue and annihilate, producing 2 gamma rays. Detectors triangulate the rays to build a 3-dimensional image of the body's metabolism. Antimatter, the most exotic substance ever predicted by theoretical physics, now scans for tumors in ordinary clinics. CERN runs an entire facility called the antiproton decelerator, where antiprotons are slowed down and combined with positrons to form atoms of antihydrogen. Each atom is the mirror version of ordinary hydrogen. Antihydrogen is held in magnetic traps for minutes at a time. Lasers probe its energy levels. As far as anyone can tell, antihydrogen behaves exactly like hydrogen in every measurable way. Yet here is the deepest puzzle. According to the basic rules of quantum field theory, matter and antimatter should have been produced in equal amounts during the Big Bang. They should have annihilated each other completely as the universe cooled, leaving behind only photons. There should be no stars, no galaxies, no planets, no reader. Instead, there is a universe full of matter, with almost no antimatter to be found anywhere. For every billion antiparticles in the early cosmos, there were 1,000,000,001 ordinary particles. After the Great Annihilation, that one extra particle out of every billion was left behind to build everything. You and your entire planet are the surviving leftovers of an incomprehensibly violent matter-antimatter war that ended in the universe's first second. What caused the imbalance is one of the great open questions in physics. 3 conditions, worked out by Andrei Sakharov in the Soviet Union in 1967, must be satisfied for matter to win. 2 have been confirmed in the lab. The third one is still unaccounted for, at the level needed. The missing piece may live inside a field we have not yet discovered, or it may live in tweaks to the fields we already know. Either way, the imbalance left a fingerprint on every atom in your body. If quantum fields really are the source of all particles, then it should be possible to make new particles by hitting a field hard enough. Pump in enough energy and a ripple will appear. The energy becomes mass. This is one of the most direct predictions of quantum field theory, and it has been confirmed thousands of times in laboratories around the world. The simplest version is called pair production. A high-energy photon, carrying enough energy in its single packet to equal the rest mass of 2 electrons, can transform into an electron and a positron when it passes near an atomic nucleus. The photon vanishes. The 2 new particles fly out in opposite directions, conserving the photon's original energy and momentum. Pure light becomes matter. This is not theoretical. It happens millions of times a day in particle accelerators. It happens in the upper atmosphere when cosmic rays arrive from deep space and collide with air molecules, creating cascades of particles. It happens near pulsars and black holes, where gamma rays can hit a magnetic field and split into pairs. The threshold energy for pair production is fixed by the masses of the particles involved. To produce an electron-positron pair, the photon must carry at least 1,200,000 electron volts, or about 1 million times the energy of visible light. This corresponds to gamma rays. Visible light photons cannot produce pairs no matter how many of them you bunch together. The energy has to be concentrated in a single packet. The reverse process is annihilation, mentioned in the previous chapter. Particle and antiparticle meet, vanish, and reappear as photons. The 2 processes are mirror images of each other in time. Run pair production backward in a movie, and you see annihilation. Quantum field theory does not care about the direction of time at this level. The same mathematical rule covers both. In 1997, physicists at the Stanford Linear Accelerator went a step further. They fired a beam of high-energy electrons through an intense laser pulse. The electrons scattered photons up to even higher energies. Those high-energy photons then collided with the laser photons themselves. The photon-photon collisions produced electron-positron pairs out of nothing but light. The team had created matter directly from the collision of 2 beams of energy. No nucleus involved. No matter to start with. Just light hitting light. This experiment, called the Bright-Wheeler process, had been predicted in 1934 by Gregory Bright and John Wheeler. They did not believe it could ever be observed in their lifetimes because the energies required were beyond anything imaginable at the time. 63 years later, technology caught up. Pair production is also why ordinary objects do not spontaneously turn into bursts of radiation. The threshold energy is high enough that the everyday world stays stable. But in the cores of the most extreme objects in the universe, neutron stars, magnetars, the accretion disks around supermassive black holes, the energy densities reach levels where pair production becomes constant. Around such objects, space itself fizzes with electrons and positrons being created and annihilated in vast quantities. There are even theoretical scenarios where intense electric fields, all on their own, could rip particle pairs out of the vacuum. This is called the Schwinger effect, named after Julian Schwinger, who predicted it in the 1950s. The required field strength is so enormous that no laboratory has ever produced one, but powerful upcoming lasers may finally cross the threshold within the next 2 decades. The first time scientists watch matter pour spontaneously from an empty region of pure electric field, the consequences for our understanding of the vacuum will be enormous. Energy and matter are not just convertible in some abstract sense. They are the same substance, taking different shapes inside the fields that shape reality. Run the clock backward to 1 second after the Big Bang. The universe was a furnace of matter and antimatter, born together in nearly equal amounts as the early plasma cooled enough to start producing particles. Quantum field theory, in its standard form, predicts they should have been created in perfectly equal pairs, every quark with an antiquark, every electron with a positron. The total balance should have been exactly 0. When such a perfectly balanced soup cooled, every particle should have eventually found its antiparticle and annihilated. The result would have been a universe filled only with photons, drifting through empty space. No atoms, no stars, no structure of any kind, forever. That did not happen. We are here. The cosmos is full of matter, and antimatter is so rare that scientists have to manufacture it carefully in accelerators just to study it. For every 10 billion antiparticles produced in the early universe, 10 billion and 1 ordinary particles were produced. After the Great Annihilation, that single excess particle out of every 10 billion was left behind. The matter we see today is the leftover residue of a near-total cosmic destruction. This single observation is the biggest unsolved problem in particle physics. Why was there an imbalance at all? In 1967, the Soviet physicist Andrei Sakharov, who would later become famous as a dissident and human rights advocate, listed 3 conditions any successful explanation would have to satisfy. The first condition is that matter and antimatter must be produced at slightly different rates by some process. The second is that the universe must go through a moment of being out of thermal equilibrium. Otherwise, any imbalance created at one moment would be undone in the next. The third is that the laws of physics must treat matter and antimatter slightly differently. In some subtle way, the technical name for that asymmetry is CP violation. 2 of these 3 conditions have been confirmed in experiments. CP violation, the deepest one, was first observed in 1964 by James Cronin and Val Fitch in the decay of certain neutral particles, called kaons. They found that kaons and antikaons decayed at very slightly different rates. The difference was tiny, less than 1 part in 1,000, but it was there. The universe is not perfectly symmetric between matter and antimatter. The problem is that the amount of CP violation observed in kaons, and later in similar mesons containing heavier quarks, is far too small to explain the matter dominance we see in the universe. The standard model can produce maybe 1 part in a quadrillion imbalance through known mechanisms. The actual imbalance was about 1 part in 10 billion. There is a gap of several orders of magnitude between what the standard model predicts and what nature delivered. Something else must have happened, some additional source of CP violation, beyond the standard model, must have tilted the balance. Physicists are searching for it in the behavior of neutrinos, in possible new heavy particles produced in the early universe, in the properties of the Higgs field itself. Several major experiments around the world are running right now to look for the missing piece. A leading candidate is leptogenesis, a process in which extremely heavy neutrinos in the very early universe decayed asymmetrically, producing a slight excess of leptons over antileptons. That excess then converted into a baryon excess through a separate quantum process called the sphaleron, leaving behind the matter we see today. The theory is elegant and fits the data, but the heavy neutrinos required have never been directly observed. Without this asymmetry, no atoms would have formed, no galaxies would have collapsed out of the early gas, no planet Earth, no reader. Your existence depends on a 1 in 10 billion fluke that physics still cannot fully explain. Quantum field theory predicts that empty space contains energy. Every field, even at its lowest possible state, still trembles. That trembling carries energy. Add up the trembling of every field at every wavelength in every cubic centimeter of space, and you get a number for how much energy a vacuum should hold per unit volume. Physicists have done this calculation many times. The result is a disaster, the largest scientific embarrassment of the past century. The straightforward calculation gives a vacuum energy density that is about 10 to the 120th power times larger than what we actually observe. That number is so enormous that there is no familiar way to picture it, a 1 followed by 120 zeros. To call it astronomical understates it severely. What does the real vacuum energy density look like? Astronomers have measured it indirectly by tracking the expansion rate of the universe and how it has changed over billions of years. They can pin down the background energy filling space. The number is small, roughly equivalent to a few hydrogen atoms worth of energy in every cubic meter of space. Not zero, but small, tiny, almost nothing. The mismatch between calculation and observation is 1 part in 10 to the 120. If quantum field theory and gravity simply combined the way they appear to, the universe would have been ripped apart by its own vacuum energy in less than 1 second after the Big Bang. Everything would have flown apart at unimaginable speeds long before any structure could form. There would be no atoms, no light, no anything. That did not happen. The universe held together. Galaxies formed. Stars ignited. The actual vacuum energy is small enough that gravity could pull matter into clumps before the expansion overwhelmed it. This problem is called the cosmological constant problem, and almost every physicist working on theoretical physics has tried their hand at solving it at some point. None has succeeded. The best attempts make some progress, then run into new problems. One approach is to assume that some unknown mechanism cancels out almost all of the contributions from the vacuum, leaving only a tiny residue. the cancellation would have to be precise to 1 part in 10 to the 120. No known mechanism delivers that level of fine-tuning naturally. The match would have to be either a stunning coincidence or the result of a principle nobody has yet identified. Another approach is to suggest that the vacuum energy is not actually what we calculate. Perhaps the calculation is using the wrong tools. Perhaps quantum field theory is incomplete and breaks down at high energies in a way that changes the answer dramatically. This is plausible, but it requires a theory we do not yet have. A third approach, more philosophical, is the multiverse idea. Maybe there are countless universes, each with a different vacuum energy. Universes with large energies blow themselves apart instantly. Universes with small energies last long enough to form structures and contain observers. We find ourselves in one of the rare quiet universes simply because no observer could exist anywhere else. This is called the anthropic explanation, and it is controversial. Many physicists consider it a confession of failure rather than a real answer. What we know for sure is that empty space does have a small amount of energy. The expansion of the universe has been speeding up over the last several billion years, driven by something called dark energy. The simplest interpretation is that dark energy is the residual vacuum energy we have been struggling to calculate. It is real. We see its effects in every direction we look. But where it comes from and why it has the value it does is one of the deepest mysteries in physics. The answer may rewrite quantum field theory entirely. Albert Einstein introduced a number into his equations of general relativity in 1917. He called it the cosmological constant, and he added it for one reason. He wanted his equations to predict a static, unchanging universe. Without the constant, gravity would pull all the matter together over time, and the universe would either expand without limit or collapse on itself. Adding the constant allowed for a perfectly balanced cosmos that neither grew nor shrank. A decade later, Edwin Hubble at Mount Wilson Observatory measured the redshifts of distant galaxies and showed that the universe was expanding. There was no need for a static balance. Einstein removed the cosmological constant from his equations. He reportedly called it the biggest blunder of his life. Then in 1998, 2 independent teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, dropped a bombshell. They had measured how the expansion rate of the universe had changed over billions of years, using a special type of supernova as a cosmic distance marker. The expected result was that the expansion should be slowing down due to gravity. Their actual result was the opposite. The expansion was speeding up. Something was pushing the universe apart, faster and faster. Whatever it was, it filled all of space with a constant energy density that did not dilute as space expanded. The simplest mathematical description of this something turned out to be Einstein's old cosmological constant, brought back from the dead. This blunder turned out to be one of the most important predictions in the history of physics, even though Einstein had introduced it for the wrong reason. The 3 discoverers shared the Nobel Prize in 2011. Now physicists faced 2 problems at once. First, they had to explain what was driving the acceleration. Second, they had to reconcile the observed value with the prediction from quantum field theory, which gave a number off by 120 orders of magnitude. The quantum vacuum should produce so much energy that the universe should have torn itself apart instantly, but the observed acceleration corresponded to a tiny, gentle, almost imperceptible push. Physicists currently call the source of this push dark energy. The label is a placeholder for ignorance. Dark energy makes up roughly 68% of the total energy content of the universe. Ordinary matter, including all stars, planets, gas, dust, and human beings, accounts for less than 5%. Dark matter, another mystery, accounts for about 27%. The everyday substance you see when you look around is a small minority of what is actually out there. The cosmological constant problem is the question of why the dark energy density is so small. From the perspective of quantum field theory, the calculation predicts something enormous. From observation, the answer is tiny. The 2 numbers should not be able to coexist in the same universe. A wide range of solutions has been proposed. Some involve symmetries that almost perfectly cancel out the vacuum energy. Some involve modifications to gravity at the largest scales. Some involve scalar fields with carefully tuned potentials. None of them has emerged as the clear winner. Recent measurements from the Dark Energy Spectroscopic Instrument, or DESI, suggest that dark energy may not even be constant. It might be changing very slowly over cosmic time, getting weaker as the universe ages. If confirmed, this would rule out the simplest version of the cosmological constant and point towards something more dynamic, a field that changes its value perhaps. A new kind of particle, something we have not yet seen. The expansion of the universe is being driven by something that may be only the second known case of a field permanently filling space, alongside the Higgs. Or it might be something entirely new. But there is another invisible substance pulling on galaxies, and we know it exists even though we have never detected a single particle of it. In 1933, the Swiss astronomer Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He measured how fast the galaxies were moving relative to each other, and was startled by the result. They were moving so fast that the gravity of the visible matter in the cluster should not have been enough to hold them together. The cluster should have flown apart long ago, yet there it was, intact and stable. Zwicky proposed that there must be additional unseen matter in the cluster, exerting gravity but not emitting any light. He called it Dunkel Materie in German, dark matter. Most of his colleagues ignored the idea for 40 years. Then in the 1970s, the American astronomer Vera Rubin made a similar discovery in individual galaxies. By measuring the rotation curves of stars at different distances from galactic centers, she found that stars at the edges of galaxies moved much faster than expected. Visible matter alone could not produce enough gravity to keep them in orbit. They should have flown off into intergalactic space. Yet they stayed. Some invisible substance was holding them in. Today, the case for dark matter is overwhelming. Every spiral galaxy ever measured has an extended halo of invisible mass surrounding its visible disk, the cosmic microwave background, the leftover radiation from the early universe, shows patterns that can only be explained if dark matter was already present and shaping the formation of structure during the first hundreds of thousands of years after the Big Bang. Gravitational lensing, where light bends around massive objects, reveals dark matter directly through its gravitational pull on light passing through clusters. The total amount of dark matter outweighs ordinary matter by a factor of about 5 to 1. For every kilogram of stuff you can see in the universe, there are 5 kilograms of stuff you cannot. What is it? The honest answer is, nobody knows. Despite decades of searching, no experiment has ever directly detected a single particle of dark matter. Every major physics laboratory in the world has hunted for it. None has caught it. The leading candidate for many years was a hypothetical particle called the WIMP, or weakly interacting massive particle. A WIMP would carry mass, but interact only through the weak force and gravity, making it almost invisible. Underground detectors, shielded from cosmic rays by miles of rock, have searched for the rare collisions of WIMPs with ordinary atoms. After over 30 years of looking, the detectors have come up empty. The simplest WIMP models are now largely ruled out. Other candidates remain. Axions are extremely light particles predicted by certain extensions of the standard model. They would barely interact with anything but might be produced abundantly in the early universe. Sterile neutrinos are hypothetical heavy cousins of ordinary neutrinos that interact only through gravity. Primordial black holes formed in the very early universe could account for some or all of dark matter without involving new particles at all. Each candidate corresponds to a possible new field hidden behind the 17 we already know. If dark matter is a new particle, it must have its own quantum field permeating space, ripples of which have been gravitating with our visible matter for the last 14 billion years. If dark matter is real and our search techniques are correct, then our current picture of the universe is missing the largest single ingredient. The dominant field in the cosmos has not yet been touched by our experiments. We see only the shadow it casts. But there is one more field that almost certainly existed, briefly, in the very first moment of the universe. And it stretched space itself. The universe is much bigger and much smoother than it has any right to be. When astronomers map the cosmic microwave background, the leftover light from when the universe was 380,000 years old, they find that the temperature is the same in every direction, to better than 1 part in 100,000. Patches of sky that were never in causal contact with each other, regions so far apart that no signal could have traveled between them since the Big Bang, somehow share the same temperature down to a fraction of a degree. This should be impossible. Heat equalizes through contact. If two parts of the universe never touched, they should not have had time to reach the same temperature. Yet the entire observable universe looks remarkably uniform. The standard solution, proposed by Alan Guth at MIT in 1980, is called inflation. Guth suggested that during a tiny fraction of a second after the Big Bang, the universe underwent a period of explosive, exponential expansion. In a time interval shorter than 10 to the minus 32 seconds, every point in space stretched apart by a factor of at least 10 to the 26th power. A region smaller than a proton became larger than the visible universe today. Inflation explains why the cosmic microwave background looks uniform. Every part of the visible universe was originally in a tiny region that was indeed in causal contact and reached thermal equilibrium. Then inflation stretched that small uniform region into the enormous nearly uniform cosmos we see now. The puzzle dissolves. The engine behind inflation is a hypothetical field called the inflaton. It is a quantum field with a very specific shape to its energy curve. When the inflaton sat at a particular value, its energy density was nearly constant in space, producing a runaway exponential expansion. As the field rolled down to its lowest energy state, the expansion ended, and the energy stored in the inflaton was dumped into the production of ordinary particles. That moment is what we usually call the Big Bang in popular language. It was less an explosion and more a sudden release of a tremendous reservoir of vacuum energy. The inflaton has not been directly detected. Its signature should appear in the patterns imprinted on the cosmic microwave background, particularly in a feature called primordial gravitational waves. Several experiments have searched for this signature. None has yet found it definitively. The BICEP team in Antarctica reported a detection in 2014, but later revised the claim after learning that interstellar dust could mimic the signal. Despite the lack of direct proof, inflation explains so many features of the universe that most cosmologists treat it as the leading model. It explains uniformity. It explains why the universe is geometrically flat, to a precision of better than 1%. It explains why magnetic monopoles, predicted by various particle physics theories, have never been observed. It explains the seeds of large-scale structure, since quantum fluctuations in the inflaton field during inflation would have been stretched into the small density variations from which galaxies eventually formed. If inflation is right, then every galaxy, every cluster, every cosmic structure traces back to quantum fluctuations of a single field. The mountains and valleys of cosmic matter visible in modern surveys are the descendants of microscopic ripples in the inflaton field, blown up to cosmic scale by a factor that staggers the imagination. The inflaton is also an example of how a quantum field can do more than make particles. It can shape the geometry of space itself, drive cosmic evolution, and seed the formation of everything we see. Fields are not just the source of matter, they are the source of structure. But there is one field that quantum field theory cannot describe, and that failure points toward a deeper theory we do not yet possess. The standard model of particle physics, built on quantum field theory, describes three of the four known forces of nature with breathtaking precision: electromagnetism, the strong force, the weak force. All three fit elegantly into the framework. Each has its own field, its own messenger particles, its own behaviors that can be calculated to fantastic accuracy. The fourth force is gravity, and gravity stubbornly refuses to fit. Einstein's general theory of relativity, published in 1915, describes gravity not as a force in the usual sense, but as the curvature of space-time caused by mass and energy. A massive object bends the space and time around it, and other objects move along the curves of that bent geometry. The theory has been tested with extraordinary precision over the past century. It predicts the precise rate at which the planet Mercury wobbles in its orbit. It predicts how light bends around the sun. It predicts the exact shape of gravitational waves emitted when two black holes merge. But general relativity is a classical theory. It treats space-time as a smooth, continuous fabric. Quantum field theory, in contrast, requires that everything come in discrete chunks. Energy comes in quanta. Charges come in fixed amounts. Fields ripple in patterns that obey the uncertainty principle. When physicists try to write a quantum theory of gravity using the same techniques that worked for the other forces, the math explodes. The calculations produce infinities at every step. Unlike in quantum electrodynamics, where similar infinities can be tamed by a procedure called renormalization, the infinities in quantum gravity multiply uncontrollably. Each new calculation requires an additional infinite correction to make the answer finite. After a few corrections, you need infinitely many additional rules, and the theory loses all predictive power. This is the deepest unsolved problem in fundamental physics. We have two theories that work brilliantly in their own domains and cannot be combined. The mismatch matters most in extreme situations. Inside black holes, at the moment of the Big Bang, in the cores of neutron stars. In any setting where gravity is strong enough that quantum effects become important, neither theory alone can answer the question. We do not know what happens at the center of a black hole. We do not know what happened in the first moment after the Big Bang, before the universe had cooled enough that quantum gravity stopped mattering. We have a wall of ignorance, precisely where the most interesting physics happens. Several research programs have tried to close the gap. String theory replaces point particles with tiny vibrating strings, and in doing so, it naturally produces a quantum theory of gravity. Loop quantum gravity treats space-time itself as made of tiny discrete loops, each one a fundamental unit of geometry. Causal set theory imagines the universe as a network of discrete events linked by causal relations. None of these approaches has produced a single experimentally testable prediction that distinguishes it from the others, although string theory has produced a great deal of mathematical machinery. The fundamental obstacle is that quantum gravity becomes important only at energies far beyond anything we can produce in a laboratory. The relevant energy scale is the Planck energy, which is roughly 10 to the 19th times the energy delivered by the Large Hadron Collider. Building a machine that could probe quantum gravity directly would require a particle accelerator the size of a galaxy. We are not going to build that machine. Some hope remains that astronomical observations of the very early universe might leave fingerprints we can read, or that the structure of black hole evaporation, predicted by Stephen Hawking in 1974, might reveal hints of the deeper theory. So far, the universe has been quiet on the subject. Quantum field theory, as powerful as it is not the final theory. It cannot describe gravity. Whatever replaces it will have to absorb everything quantum field theory has taught us and add something new. We do not yet know what. Take everything we have learned about quantum field theory and stitch it together. Combine the 17 fields, add the rules for how they interact, pin down their masses, their charges, and their coupling strengths. The result is the standard model of particle physics, the most precisely tested scientific theory in human history. The standard model is a portrait of the universe drawn from a small number of ingredients: 6 quark fields, 6 lepton fields, 3 force carrier fields covering electromagnetism, and the weak and strong forces, 8 gluons treated together as one for counting purposes, and 1 Higgs field. These fields and their interactions describe nearly everything you see, touch, eat, breathe, and stand on. With one critical exception, which is gravity. The model predicts thousands of measurements with near-perfect accuracy. The magnetic moment of the electron has been measured to 1 part in a trillion, and the standard model prediction agrees to that same level. The mass of the W boson, the rate of certain rare particle decays, the production cross-sections of various particle combinations at the LHC, all match the theory to within experimental uncertainties. There has never been a confirmed laboratory measurement that contradicts the standard model. Hints of cracks appear from time to time. The muon's magnetic moment showed a small deviation in measurements at Fermilab in 2021. The lepton flavor universality of B meson decays has shown some tension. None of these has yet reached the threshold for a confirmed discovery. The standard model was completed, in a sense, in 2012 with the discovery of the Higgs boson. Every particle the theory predicted has now been observed. Every interaction has been confirmed in some form. The portrait is complete. Yet physicists know it is incomplete in deeper ways. The standard model says nothing about dark matter, which makes up most of the matter in the universe. It says nothing about dark energy, which dominates the total energy budget. It cannot explain the matter-antimatter asymmetry. It cannot incorporate gravity. It does not predict the values of its own parameters, instead requiring 19 of them to be measured experimentally and entered by hand. Why are there exactly 3 generations of matter particles, with each generation heavier than the last. The first generation, made of up quarks, down quarks, electrons, and electron neutrinos, builds all the ordinary matter you see. The second and third generations exist but are unstable and decay quickly. They show up at the LHC and in cosmic ray collisions. Why 3? Why not 2? Why not 5? The Standard Model has no answer. Why does the electron weigh what it does? Why does the top quark weigh nearly 200,000 times more? The pattern of masses spans an enormous range, with no obvious explanation. The Higgs coupling strengths are simply different for each particle, and we do not know why. Why do neutrinos have any mass at all? The original Standard Model said they should be massless. Then, in 1998, experiments at Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada showed that neutrinos do have a tiny mass, less than 1/1,000,000th that of the electron. The Standard Model had to be patched to accommodate them. Where their mass comes from, and why it is so absurdly small, remains an open question. The Standard Model tells us how the universe works at a level of detail no other theory has ever matched, but it does not tell us why. The values it requires are inputs, not outputs. Beyond it, there must be something deeper. The hunt for that deeper layer is the central project of modern theoretical physics. Theoretical physicists have spent half a century trying to extend the Standard Model. They have proposed grand unified theories in which the strong, weak, and electromagnetic forces all merge into a single force at extremely high energies. They have proposed supersymmetry, in which every known particle has a heavier hidden partner. They have proposed extra dimensions of space, curled up so small we cannot detect them directly. None of these proposals has yet been confirmed. Grand unified theories have a strong appeal. They suggest that the three forces we observe in the Standard Model are all manifestations of a single underlying force, frozen into different shapes by symmetry-breaking events in the early universe. The simplest version was proposed by Howard Gagé and Sheldon Glashow in 1974. It predicted that protons should be unstable, decaying very slowly into lighter particles over a timescale of about 10 to the 32nd years. Underground detectors in old mines watched massive tanks of water for the rare flash of a decaying proton. After decades of looking, no decay has been seen. The simplest unified theory is now ruled out, but more sophisticated versions remain alive. Supersymmetry was even more ambitious. It proposed that every fermion in the Standard Model, like the electron and the quarks, has a partner boson, and every boson has a partner fermion. The partners would be heavier than the originals, which is why they have not been observed. Supersymmetry would solve several theoretical problems at once. It would naturally provide a candidate for dark matter. It would help stabilize the Higgs mass against quantum corrections. It would clean up the math of grand unification. The Large Hadron Collider was widely expected to find supersymmetric partners. The simplest versions predicted partners at masses well within the LHC's reach. After more than a decade of running, nothing has been found. Each new round of data pushes the expected partner masses higher. Many physicists who staked their careers on supersymmetry have begun to acknowledge that the simplest versions are dead. Extra dimensions are another popular idea. The Standard Model lives in 3 spatial dimensions plus 1 time dimension. String theory and several other extensions require additional spatial dimensions, perhaps as many as 6 or 7, curled up so tightly that they are too small to notice. Particles propagating through these hidden dimensions would appear as new types of particles in our 4-dimensional view. Searches at the LHC for such particles have come up empty. The extra dimensions, if they exist, are smaller or more strongly hidden than the simplest models predicted. This pattern has produced what some call the crisis of particle physics. The Standard Model works flawlessly. Beyond it, every direction we have looked has shown nothing new. We know there must be more, because the Standard Model cannot explain dark matter, dark energy, the matter-antimatter asymmetry, or gravity. Yet our experiments have not yet revealed what that more is. Some physicists argue for ever larger colliders, machines that could reach energies 100 times beyond the LHC. CERN is currently planning a successor, the Future Circular Collider, a 60-mile underground ring that would dwarf its predecessor. China has proposed a similar machine. Both projects would cost tens of billions of dollars and take decades to build. Others argue that the path forward lies elsewhere. Precision experiments measuring the electron's electric dipole moment to extraordinary accuracy, underground detectors searching for dark matter, astronomical observations probing the first instance of the universe through gravitational waves, tabletop experiments testing the limits of quantum mechanics in macroscopic systems. The frontier is no longer one well-lit highway. It is many narrow paths. We do not know which one leads forward, and we are walking down most of them at once. In 1968, an Italian physicist named Gabriele Veneziano was studying the strong force, trying to understand the patterns by which heavy particles interacted at high energies. He stumbled across a mathematical formula written by Leonhard Euler 2 centuries earlier, the Euler beta function, that strangely matched the data he was trying to explain. Nobody knew why an old piece of pure mathematics should describe particle physics. Veneziano was puzzled and intrigued. Within a few years, several physicists had figured out what the formula was actually describing. It was the math of a vibrating string. If you assumed that the particles inside a proton were not point objects, but tiny stretched strings, the strange formula made perfect sense. The strings could vibrate in different modes. Each mode would appear as a different particle. This was the birth of string theory. It started as a model of the strong force, was set aside when quantum chromodynamics turned out to fit the data better, and then was revived in the 1970s when researchers realized that string theory naturally produced a particle behaving exactly like a graviton, the hypothetical messenger of gravity. This was a stunning result. Quantum field theory could not produce a sensible quantum theory of gravity. String theory produced one automatically. If you tried to compute scattering amplitudes for gravitons in string theory, the math behaved beautifully. The infinities that plagued quantum gravity in the field theory framework simply did not appear. The price of this success was high. String theory required extra spatial dimensions, 10 in total, 6 more than we observe. It required supersymmetry to be consistent. It came in 5 different versions, each requiring different rules, and calculations were extraordinarily difficult, often impossible to complete without enormous mathematical machinery. In the 1990s, Edward Witten at the Institute for Advanced Study in Princeton showed that the 5 different versions of string theory were actually different views of a single deeper theory, which he called M theory. The M stood for whatever each researcher wanted: magic, mystery, mother. M theory lived in 11 dimensions and contained both strings and higher dimensional objects called brains. For a while in the 1990s, string theory looked like it might be the final answer. It claimed to be a theory of everything, capable of incorporating all known forces, including gravity, into a single framework. A generation of bright young physicists devoted their careers to it. The problem is that string theory has produced no experimental predictions that distinguish it from other possibilities. The energy scales required to see strings directly are far beyond any conceivable accelerator. The theory has so many possible solutions, perhaps 10 to the 500th different ways to compactify the extra dimensions, that almost any low-energy physics could emerge from some version of it. With so many possible answers, the theory has trouble making sharp predictions. Some physicists treat string theory as the only game in town and continue refining it. Others have grown skeptical and turned to alternatives. Loop quantum gravity, asymptotic safety, causal dynamical triangulations, all offer different paths forward. None has yet decisively beaten the others. What remains true is that quantum field theory in its current form cannot be the final word. It works so well in its domain of validity that it must be capturing something deep about the universe. But it cannot include gravity, and the world we live in obviously contains gravity. Some larger framework is needed. Strings might be the answer, or they might be a dead end that taught physicists important mathematics on the way to something else. The verdict is still out. After more than 50 years, string theory remains the most ambitious attempt in physics to unify everything, and also the most uncertain. If quantum field theory describes the universe in terms of fields locked into specific values, an obvious question follows: could those values have been different? Could there be other universes where the Higgs field or any of the other fields settled into different states, producing different physics, different particles, different stars and chemistry? Perhaps no observers at all? The standard model alone cannot answer this. It takes the values as given, But several extensions of physics suggest that what we call the laws of nature are not absolute. They are local conditions, frozen in by the choices the early universe made as it cooled. The Higgs field is the clearest example. As discussed earlier, the Higgs field locked into its current value during electroweak symmetry breaking, an event that happened about a trillionth of a second after the Big Bang. The value it picked determined the masses of every particle in the Standard Model. A different Higgs value would have produced electrons of different mass, quarks of different chemistry. Most chemistry as we know it would not exist. The cosmological constant is another example. The tiny positive value of dark energy could have been much larger or much smaller, with dramatically different cosmic histories. A larger value would have torn the universe apart before galaxies could form. A smaller value, especially a negative one, would have caused the universe to recollapse long before life could appear. In string theory, the situation gets more extreme. The theory has, as mentioned, an enormous number of possible vacuum states, each corresponding to a different set of physical laws. Estimates of the number of solutions range from 10 to the 500th to 10 to the 1000th. If each solution corresponds to a possible universe, then there are far more possible universes than atoms in the visible cosmos. The space of possible physics is staggeringly vast. Some physicists, including Leonard Susskind at Stanford, have proposed that all of these possibilities are realized somewhere in a vast multiverse. Each solution describes a region of a much larger reality. We find ourselves in the region we are in because the parameters happen to be compatible with the existence of observers. In regions where the parameters were incompatible, no observers exist to notice. This is the multiverse interpretation, and it is controversial. Critics argue that it explains too much by explaining nothing. If everything is possible somewhere, then no specific feature of our universe needs a deeper explanation. Defenders argue that the alternative, treating our specific values as cosmic accidents, is even less satisfying. Whether or not the multiverse is real, the observation stands. The values of the parameters in the Standard Model and in cosmology have specific numerical values, and physics has not yet explained why those values rather than others. Either there is a deep reason hidden behind the Standard Model that we have not yet found, or the values are essentially random outcomes from some larger process. André Linde at Stanford has developed a related theory called eternal inflation. In this picture, the inflaton field never fully stops driving expansion in some regions of the universe. Pockets where inflation ends become bubble universes, each one with potentially different physical laws determined by how the various fields settled in that region. Inflation continues forever in the larger space, constantly producing new bubbles. We live in one bubble. The total number of bubbles is unbounded. There is no observational test that has yet confirmed or ruled out eternal inflation. Some hints might appear in the cosmic microwave background in the form of subtle imprints from the collision of bubbles. None has been definitively detected. What is clear is that quantum field theory, taken seriously, opens the door to a universe far stranger than the one we directly observe. The fields define everything, and the fields, perhaps, were free to settle into many different shapes. Ours is one frozen possibility among countless others, or perhaps simply one. We do not yet know. But there is one possibility that should give anyone pause. If the Higgs field is in a frozen state that is not actually the deepest stable state, our universe might be living on borrowed time. Recall the way the Higgs field froze into its current value during electroweak symmetry breaking. The field picked a particular value out of a range of possibilities and locked into it across all of space. Today, that value is roughly 246 geoectone volts, and it gives every particle in the Standard Model its mass. Here is the disturbing part. Detailed calculations by physicists, particularly studies based on the measured masses of the Higgs boson and the top quark, suggest that the current Higgs value may not be the deepest possible energy state. There may be another value much higher where the Higgs field could settle instead. If so, the universe is sitting in what physicists call a metastable state. It is stable enough to last a long time, but not infinitely. The technical analysis was carried out in detail after the Higgs discovery in 2012. Researchers used the measured Higgs mass of about 125 gigaelectron volts and the measured top quark mass of about 173 gigaelectron volts to calculate the shape of the Higgs field's energy curve at very high energies. The result placed our current vacuum on the edge of a precipice. Slight changes in the masses would push the vacuum into outright instability. As it stands, the universe appears to be in a metastable state with a long but finite lifetime. If the Higgs ever found a way to tunnel into the deeper state, the consequences would be catastrophic. A tiny bubble of new vacuum would form, with the Higgs at its lower energy value. Inside the bubble, the masses of all particles would be different. Atoms could not form, stars could not exist, chemistry would dissolve. The bubble would expand outward at the speed of light, converting all of space and matter in its path into the new state. There would be no warning. No light could outrun the bubble wall because the wall itself moves at light speed. Anyone caught in the path would simply cease to exist when the bubble reached them. The transition would be instantaneous from their perspective and final. This scenario is called vacuum decay or false vacuum decay. It has been considered seriously by physicists since the 1970s when Sidney Coleman and Frank DeLucia worked out the math. Their calculations showed that even a tiny bubble of true vacuum could grow without limit if it nucleated through quantum tunneling. The good news is that the calculated probability of vacuum decay happening anywhere in the observable universe within a timescale of trillions upon trillions of years is essentially zero. The barrier between our metastable vacuum and the deeper state is enormous. Quantum tunneling rates depend exponentially on the height of the barrier, and this barrier is high enough that the universe could last vastly longer than its current age before the first bubble nucleates. The bad news is that bubbles can nucleate anywhere. Statistically, somewhere out there, far beyond our cosmic horizon, the universe may already have begun decaying. If that bubble formed billions of years ago, it might be expanding toward us right now. We could not see it coming. Light from inside the bubble cannot escape it, so we would have no warning until it arrived. There is also a more disturbing wrinkle. Some calculations suggest that high-energy events could trigger nucleation, cosmic ray collisions, neutron-star mergers, even highly energetic particle collisions in laboratories. The probability is extraordinarily low enough that we have observed many such events in the natural universe over 14 billion years without any decay starting. But the probability is not exactly zero. Each event is a tiny lottery ticket. Vacuum decay is a real prediction of quantum field theory applied to the measured values of the Higgs and top quark masses. It is not science fiction. It is the boring extrapolation of equations physicists trust enough to use for everything else. Whether the universe will end this way, nobody knows. The decay might never happen, or it might be happening right now, just outside the range of our telescopes. After 32 chapters across the strangest territory in physics, here is the picture we are left with. The universe is not made of objects. There are no marbles, no atoms in the literal sense, no fundamental specks of stuff. Everything that exists is a pattern in a deeper substance we cannot see. That substance is the collection of quantum fields. Roughly 17 of them, layered into the same volume of space, vibrating constantly, producing the appearance of matter and forces and light. What we call particles are ripples. What we call empty space is a foam of virtual particles flickering in and out of existence. What we call mass is the way certain fields stiffen when coupled to the Higgs field, raising their minimum vibration frequency. What we call forces are exchanges of ripples between fields. What we call U is a temporary, self-organizing pattern of electron, quark, and photon ripples held together by the strong, weak, and electromagnetic forces, all wrapped in the dust of Higgs-derived mass and bound energy. This picture is not an interpretation. It is the framework that has produced the most accurate predictions in the history of science. The magnetic moment of the electron has been calculated to 1 part in a trillion. The mass of the W boson, the rate of subtle particle decays, the production rates of the Higgs boson all match theory to within experimental uncertainty. It is also a picture that humbles every casual assumption about reality. Solidity is an illusion produced by the electromagnetic interactions of mostly empty atoms. Permanence is an illusion produced by the slow timescales of decay and the stability of certain field configurations. Identity is shared by particles separated by billions of light years, simply because they are the same field vibrating in different places. The picture is also incomplete. Quantum field theory cannot include gravity. It cannot explain dark matter or dark energy. It cannot tell us why the matter-antimatter balance was broken in the early universe, or why neutrinos have such tiny masses, or why the various coupling constants take the values they do. The Standard Model, for all its triumphs, requires 19 parameters to be measured experimentally and entered by hand. There must be a deeper layer. Whether that layer is string theory, loop quantum gravity, some unified field theory we have not yet imagined, or something stranger, no one can yet say. The evidence for it is indirect. Its outline shows in the cracks of what we already know. And yet there is something philosophically remarkable about how far we have come. A century ago, the very idea of a quantum field would have seemed like mysticism. Today, an array of detectors 300 feet under the Swiss countryside routinely measures the production of Higgs bosons, ripples in the field that gives mass to the universe. Detectors deep in mines watch silently for the rare collisions of dark matter with ordinary atoms. Telescopes scan the cosmic microwave background for hints of inflaton fluctuations imprinted in the first moments of time. We are, in a real sense, listening to the music of the universe. The 17 songs of the 17 known fields, the interference patterns where they overlap, the deeper harmonies hidden behind them which we have not yet learned to hear. Quantum field theory tells us that reality is not a thing, but a process, not a stage on which events unfold, but a vast vibration that is the events themselves. There is no separation between the dancers and the dance. The universe is fields all the way down, and the fields are doing their work, whether we watch or not. That is what a quantum field really is, and that is why reality needs them. Without the fields, nothing exists. With them, everything is music.